Um, Good evening, Professor. This is Study Group 15, and we're going to have a video presentation on spike intelligent scheduling of Hubble's space telescope observations, and our teammates Dekul Salahuddin Rohini and myself Vijay was going to give this presentation. Next slide, please. So first, in the first slide, we're going to introduce what is spike. Spike is general framework for scheduling. Spike was developed by an organization known as Space Telescope Science Institution for NASA's Hubble Space Telescope. HST stands for Hubble Space Telescope. And the features of spike are flexibility, generality. Spike uses constraint direct search. Spike system, a broad framework for scheduling created by Space Telescope Science Institute for NASA's Hubble Space Telescope. The scientific community values efficient use of astronomical observation, since demand for research-grade telescope far outnumber supply. Because of their high cost, limited number, and the unique scientific potentials, space-based facilities have a particular need for effective scheduling. The Spike scheduler was created for the Hubble Space Telescope, but it was built for generality and flexibility, and it has subsequently been used for a variety of astronomical scheduling challenges as well as non-astronomical applications. While Spike's broad methodology was inspired by the scheduling paradigm of constraint-directed search, Spike uses multi-start stochastic pair. Hubble's Space Telescope scheduling was launched in April 1990. Features of scheduling. HST scheduling will be useful in astronomical research. Unsurpassed combination of wavelength coverage and angular resolution. Main camera was replaced by the second generation equipment. Due to its unrivaled combination of wavelength coverage and angular resolution, the HST, which was launched in April 1990, has brought crucial new capabilities for astronomical research. Despite a manufacturing fault in the primary mirror, HST is pursuing a comprehensive research program that was yielded a number of promising discoveries. In late 1993, the space scheduling will service the HST to correct the mirrors figures and replace the main camera with a second generation equipment. These modifications will restore the telescope's optical quality of its original state. Next slide, please. Now we're going to see the various constraints of Hubble Space Telescope. Precedence, minimum time separations, maximum time separations, ordering, interruptibility, repetition. The proposers may require an observation to be taken while HST is in the edge shadow or constrain the orientation of an instrument's aperture respect to the target. Proposers can label exposures as conditional or select to enable flexibility. Conditional exposures are dependent on another exposure in the observing program, or in some situations the results of grounded-based observation. The proposer must notify the STLCL that the requirement has been met before these exposures can be planned. The choose feature also allows the proposers to indicate multiple sets of exposures from which one or more will be chosen for execution. The exposures contained in the select sets will be placed on a timeline only when the conditional exposures have been completed. And we're going to see the resource constraints in this slide. There are amount of observing time, amount of data limitation, onboard tape recorder storage, command computer storage. Despite the fact that HST is mainly pre-planned with schedules set around 2 months in advance of execution, schedule delays occur for a variety of reasons. The most welcome disruptions are what are known as targets of opportunity, which are quite uncommon. Important astronomical occurrences that must be attended to right away. Example, supernova. Other spacecraft abnormalities, loss of communication links, and other factors might cause scheduling interruptions, as well as modification in monitoring programs. Next slide, please. Now we will see the representation and combination of constraints and preferences. Feasibility constraints, conditions or times when activities may or may not be arranged are defined by the feasibility restriction. This type of constraint is referred to as strict or hard constraint because it cannot be violated under the normal circumstances. Preference constraints. Preference constraints define quality judgments on scheduling conditions that are desirable but not necessary. These may be based on objective or subjective considerations. Examples of feasibility constraints. Allow at least 2 months between an initial observation and a follow-up observation on the same target. And one more example, when the sun is within 50 degrees of target, never arrange an observation. The spacecraft should not be rolled more than 30 degrees from its normal orientation. The examples of preference constraints. Decrease scattered light from the Earth's bright limb. Increase the likelihood of acquiring the guide stars. And the last example is place an observation as close to the nominal role as possible. Next slide. Suitability functions. Number of constraints acting on a task. So combination of application constraints are needed. However, because a continuum of scheduling conclusions must be evaluated, the methodologies utilized in the rule-based system for evaluating evidence for or against discrete conclusions cannot be easily applied to scheduling. Example, schedule at, etc. Instead, a continuous version of uncertainty reasoning is necessary, stated in such a way that it effectively represents the range of constraints that commonly exist in these problems, while also retaining knowledge about choices that affect schedule optimality. A method for combining information from two or more independent constraints is central to this concept. Preference combination and suitability function. Procedures utilized in a rule-based frameworks for assessing proof for or against discrete conclusions cannot be connected specifically to planning. Outline of suitability functions for case of binary preference constraint. You can see on the right hand side of the slide. An inclination communication that a task ought to be planned as before long as conceivable after minutes from the completion of another assignment, and in no case avoids that then minutes. Speculative reasonableness of a few organizations within the planning handle. The coming about the suitability of the intervals where each work is non-zero are demonstrated by bars under the time axis in B and C. Suitability functions give a straightforward but viable system for capturing metric time, scheduling limitations, both strict and inclination. Such a probabilistic characteristic that comes about of planning as an input to the planning operator differs from the reasonableness work point of view. From here on, Rohini will take over. Thank you very much.
Thank you, Vijay. Now let us look into the HST scheduling as a constant satisfaction problem. A CSP is made up of a set of variables where each having a discrete value domain and a set of constraints, and this task at hand is assigned to the constant set of values to all the variables where no constraints are broken. And to convert this scheduling programming into CSP, we assign a variable to each activity to be planned and divided the scheduling time range from each activity into intervals that corresponded to the domain of the corresponding variable. And we have a broad toolkit developed by the Spike for representing and handling constraint satisfaction scenarios. And this toolset is used by the Spike scheduling search method. And this CSP is commonly expressed and considered only tight constraints and ignore preferences. However, we can add the problems, the requirement that preference to be maximized in the solution state. Now let us look into the Spike CSP toolkit. The Spike CSP toolkit consists of a collection of object classes and methods. The most essential of which are abstract classes are for CSP and variables, whereas CSP stands for the constant satisfaction problem, and it refers to the collection of variables, constraints, and other factors which are needed to fulfillment the problems. And variable where the assigned values, disputes, preferences, and so on are represented by the variables. And the CSP toolbox has a number of essential capabilities, including inconsistent assignment, locked and ignored variables, removal and restoration of domain values, constraint weights, constraint catching, assignment history and snapshot, and we have a capacity constraint also. Now let us look into the time sampling. As previously stated, the CSP variable domain discreted the schedule interval from an activity, and as a result, it considers how to discrete temporal representation. And in general, for the major changes in scheduling constraints, the sample intervals must be shortened than the period. If this requirement is met, the next step is choosing a sample technique that specifies how to handle the straightening constraint. The main fundamental decision is whether or not exclude the full interval is if the full period is excluded or workable solutions may be missed. If the interval is not included, the scheduler may identify what looks to be feasible configuration, but it not when the timing is inspected in detail. Now let us look into the scheduling search in Spike. In Spike uses multi-start start-state repair and heuristic repair-based scheduling search tool to approach scheduling construction as a limited optimization problem. And we have a following steps in this technique. There are trial assignment, repair, and deconflict. And this search procedure is influenced by two or more factors. Those are the optimization and over subscription. Now let us look into the trial assignment heuristic and the repair heuristics. To discover the most effective combination of the variables and the value selection heuristic for repair-based techniques, we consider the extensive trials on various combination of variables and value selection heuristic. Spike repair heuristics are based on the successful neutral network architecture designed specially for the Spike and then enhanced into a simple symbolic form, and now replace it the neural network. Now let us look into the deconflict, scheduling quality measures, and the rescheduling. The Spike currently uses a simple mechanism for removing the conflicting activities from an overcrowded scheduling, and as well as eliminating activities are selected based on their lower priority and higher number of constraint conflicts. And the overall observing time scheduler, the number of observed on the schedulers, and the cumulative degree of preferences of the schedule observations, all are the important schedule quality measures. And this Spike helps with rescheduling in a variety of ways. We have a task looking and the conflict cause analysis are the two features of CSP toolbox, which are a worthy discussion. And next slides will go on to conclude by our teammate. Thank you.
Yeah, thank you so much, Ronini. That's a good presentation. So now I'll be talking about the Spike and the HST science scheduling. Spike planning and scheduling was developed to support of the Hubble Space Telescope as a general toolkit of planning and scheduling under the contract NAS 5-26555 with the National Aeronautics and Space Administration, as well as Vijay already spoke about in the first slide. So, and the goal of this toolkit is to promote scientific research through the effective and efficient use of ground and space-based astronomical observation. So, looking at this activity on Spike, like Spike is an activity-based AI scheduler, which incorporates innovative approaches to constraint representation and reasoning and scheduling research. Although developed for space telescope scheduling, but the Spike system was also designed around a general scheduling constraint framework that can be applied to other domains. So the Sky scheduling system developed for scheduling astronomical observation for NASA Hubble Space Telescope (HST), which is described. The spike is an activity-based, as I said earlier, with incorporating an innovative approach to constrain representation and reasoning and scheduling research. Next slide, please. Now, looking at the spike scheduling framework. So the spike is a general framework for planning and scheduling, which its capability include a powerful yet efficient method, which is suitable function to represent the wide variety of strict and preferential constraints encountered in real scheduling problems. We have also capable of a long and medium and short term ground-based telescope scheduling, and also the long and short term orbiting spacecraft scheduling. And we have the absolute constraint, that is the observation at the time x, and also the relative constraint, which is A after B by X days. So constraint satisfaction problem, CSP based scheduler, and also capable of powerful, customizable, automatic scheduler based on this multi-stat stochastic repair technique. Now, just a little brief on what are the capabilities of the spike scheduling framework. The long and short-term scheduling tools, known as the LTS and the STS, are part of the ESO Observation Handling System, OHS, a collection of tools from processing and managing observing proposal and also observing schedules and observing sequence in the form of observation blocks, OBS. So the long-term scheduling is used twice a year to analyze the characteristics of an accepted set of observing proposal and to propose a 6-month schedule. And the short-term schedule is used nightly to produce observation block execution sequence timeline that minimize operations overhead against to user selectable set of weather condition, instrument configuration, and also scientific priority. So the absolute constraint is a variation that concentrates on one or more dimension of phenotypic space and entirely devoid of variation, which this means that evolution cannot proceed in those directions, and absolute constraint seems to rear in excess population. So relative constraint is when the variation is concentrated mainly on one direction, but there is more variation in all directions, and thus there is an evolutionary response to selection in all directions. Although some direction produce bigger response than others, the situation is common for shape and other morphological traits. Next slide. Continuation on spike scheduling framework. So spike scheduling, planning and scheduling system capability are still not limited to the resource constraint, which is talking about the data volume, a number of real-time contents, etc., and the fast, efficient constraint propagation and scheduling algorithm. And we also have the queue, which is the interleaved and the batch scheduling. And we have the library of mathematical, time, astronomical, and graphical display utility function. So a resource constraint is any limitation and or risk associated with project resources. Identifying this resource management constraint is part of the project planning phase, such as data volume, number of real-time contents, and resource constraints are roadblocks that can derail your project and prevent successful delivery. Now, looking at the queuing process, the queuing process is a model of waiting lines. The queuing process, can you go back? Yeah, the queuing process is a model of waiting line constructed so that queue lengths and waiting times can be predicted. And the batching scheduling, this is a scheduling and execution of series of jobs in the background batch mode without any human interaction. Next slide, please. So the spike for Hubble Space Telescope HST, like how does spike work for the Hubble Space Telescope HST? So the Hubble Space Telescope HST is also a NASA ESA funded project that was launched into orbit in 1990, April 24, on the Space Shuttle Discovery from Kennedy Space Center in Florida. And Hubble Hubble has made more than 1.2 million observations since its mission began in 1990, and astronomers using Hubble data have published more than 14,000 scientific papers, making it one of the most productive scientific instruments ever built. Hubble does not travel to stars, planet, or galaxy. It only takes pictures of them at its wheels around Earth at about 17,000 miles per hour. So the Space Telescope Science Institute managed this solicitation of science program, planning and scheduling, and data archiving for HST. Therefore, HST consists of long-range plan and short-range plan. The long-range plan is at approximately 8 months long, and it's updated nightly to ensure that it's kept current observation are assigned current to keep it current. And observation are assigned a planned window, which is usually about 2 months long, but can be smaller due to observation constraint. So the HST short-term schedule are 7 days in length and are created from the variable pool of long-range planned candidates whose plan window overlap and current scheduling period. So such like the long-range planning software, the short-term scheduler supports astronomical event calculation, constraint modeling, then also the absolute relative resource, and both manual and automatic scheduling. And the output from the short-term scheduler is a time order activity list, that is slews, guide star acquisition, and target time, etc. Next slide, please. Now the HST usage of Spike. So Spike is used for Hubble Space Telescope operation in several areas. As part of the Remote Proposal Submission System, RSPS2, both there's a quote from this RSPS2 and Bosser et al. In 1995. It is used by astronomers to specify observation with the HST. The RSP2 is a software tool which provides feedback on various aspects of Hubble observing proposal as it's being prepared for submission to the STSCL. Spike also uses within RSP2 to provide information on the schedulability of observations based on the implicit and explicit constraints that have been specified on the observation. Also, Spike is used for proposal implementation in the STSCL. So Spike also used to create the long-term HST observing plan, which assigns the plan window to observation. So now we're gonna take a little bit look about this mini table here in the Spike application and the explanation. So like the adaptation of Spike from this problem in the table demonstrates in the picture above is the flexibility of the scheduling framework as indicated above, and Spike was designed so that new tasks and constraints can be defined without changing the basic framework. So for some applications, Spike is operated in an hierarchical manner with long-term scheduling, first allocating the observation to weeks, much as there are for the HST problem, and with similar types of long-term constraint and preference. Next slide, please. So now planning, why do you use of Spike planning and scheduling tools? Why do we use Spike as planning and scheduling tools? So the planning and scheduling is necessary to improve the quality and efficiency of science observation, and also planning and scheduling is also important to enforce observing constraints such as observing windows, phase requirements, and timing links between observation. And observation efficiency can be improved by maximizing the number of high-quality observations made, minimizing the time takes to execute observation, minimizing waste observation, and optimizing the use of limited resources. And scheduling tools also enhance the ability to effectively react to changes in observing conditions such as times of excellent seeing. So computer-based planning and scheduling tools can significantly improve the quality and efficiency of science observation. There is a quote by Johnston, 1993 report. According to scheduling has been controlled in space astronomy for years. Based on Johnston and Miller 1994 report, but it's relatively new to much of the ground-based community. So now in conclusion, so we come in conclusion that like this, the Space Telescope Science Institute developed the spike planning and scheduling software in support of the Hubble Space Telescope as a general toolkit for planning and scheduling. And they desire to provide a spike to order observation to ease the task of planning and scheduling of observation and consequently promote astronomical research. Then constraint can be classified into three categories, which is scientific, operational, and resource constraint. And scientific constraint are specified by the observer. For example, an observation might have a phase constraint determining when it may be executed, or spectrographic slit may require a certain orientation with respective to a galaxy. Then the operational constraint come into play from the limitation imposed by the way the telescope is operated. For example, an HST observation requiring a communication link can be executed only when the communication satellite is visible. So then looking at the resource constraint, this comes into play when an observation makes use of one or more observatory resources and there are limitations on resource usage. For example, some HST observation dump data to a tape recorder, and so there are data rates and data volume constraints. So Spike provide a means to express these constraints and calculate the total effect of constraint on the observation. Spike also can be used for both short-term and long-term scheduling. And there is no intrinsic time granularity built into the software. And Spike Future is a powerful and flexible scheduler which can be optimized for different scheduling problems. And last but not the least, which is it supports rescheduling by providing functions to lock observation in place by the ability to specify conditional observation and by the scheduling algorithm. We come to the end of the presentation. Thank you so much, Professor David, for giving us the opportunity doing this group research. And me and my team member, we are able to come into this study exercise and view our own understanding about this presentation. Thank you very much, Professor.
Thank you, Prof.